Welcome to a read along with Dr. Pal in the book Discrete Perspectives in Mathematics. This is subsection 5.2.3, lifting our isomorphism to free Z modules. So we talked about an isomorphism that, in fact, this is a module isomorphism, preserves outside multiplication as well as group structure between two groups. This one, which is like the problems or the congruences that we want to solve, and this one that has the solutions, Z mod 12Z and Z mod 3Z cross Z mod 4Z, for instance. Okay, so in the last subsection, we talked about how this isomorphism was really an R module isomorphism. And now we're going to study what this isomorphism looks like in another sense when it's lifted to what's called a free Z module. So the group, for instance, the group Z mod 12Z is a Z module, but it's not free in the sense that things are tied down a little bit. Things are chunked up. You're dealing with kind of a modding out idea. And that is kind of the opposite of this idea, this word here, free. Free means like free from modding almost in some sense. So let's take a look at what this looks like. All right, so let's just see what the text says. Okay, so we have, okay, that all and no other x do. So in our isomorphism f of this last subsection, so that one, all right, all x in this fiber, okay, -1. So this is all integers in here. So this is like a subset. So now, right now, let's think about this like as identify it with its pre-image in the modding map. So just in the integers themselves. And so basically everything that's one less than a multiple of 12. So take anything that's one less than a multiple of 12 and it'll satisfy this. It'll be 2 mod 3. I mean, even think about it, 11 itself, right, is 2 more than 9, so that works there. And 3 more than a multiple of 4, and indeed it is, it's 3 more than 8, here 11. But not just 11, but any x in here will actually satisfy this. Now, why is this true? It's because this isomorphism was an isomorphism between Z mod 12Z itself and Z mod 3Z and Z cross Z mod 4Z. So, so really, this idea, this x can be changed out by anything that is congruent to -1 mod 12, and we would be good with our solution. So really, there's a lot of things happening in the integers themselves. So kind of lifting things back to the integers, looking at representatives of the fibers. That's kind of where we're going to be heading. Okay. Also, okay. All right. So this guy gives a solution to this. This guy gives a solution to that. And we saw that before because here we're going from congruence to solution. All right. Okay, we can compare group tables to see that they're isomorphic, but what if we don't want to write out a whole group table and exactly look out? Is there a rule or something we can use to see how things are isomorphic and how that works? Let's kind of think about what's happening. This right here is a merge of Z cross Z. So if we, in the first component, mod out by 3Z, and the second component mod out by 4Z, that's you're merging. We're merging, we're quotienting Z cross Z, and Z cross and Z mod 12Z is a merge of Z. All right, we want a map like this, but let's consider this map before we merge, before we mod, when it just looks like this: Z cross Z to Z. Okay, so let's just look at a map that's up here at this level instead of a map that's down here after quotienting out, which is what we've been working with. Let's pull the whole picture back up here to Z cross Z to Z. All right, So let's label E1 as 1, 0, E2 is 0, 1, kind of thinking components here. So they live in the domain of H. And okay, so any AB up here actually has a unique representation like this. So AB is equal to A times E1 plus B times E2. You could think of this as a linear combination, if you'd like, of E1 and E2. You could almost think of E1 and E2, if you've had linear algebra, you could think of them as being like standard basis vectors, or if not, that's fine. They're just tuples where you have one appearing and everywhere else you have zeros, a zero and another one. They're just like tuples or vectors in here. So, but we can see that AB is uniquely represented by a sum of E1 and E2 in this way. If we multiply E1 by A and E2 by B. Quite literalist, think about that. If you take A and you multiply it to 1, 0, you're going to get A0. If you take B and you multiply it to E2, you're going to get 0B. So you have A0 plus 0B, and you add component-wise. So A plus 0 in the first component, and then you have 0 plus B in the second component. Okay, so Z cross Z and Z themselves are Z modules. They have outside Z multiplication, because it's the same thing as the multiplication within itself, at least for Z. And here it's simple. The multiplication just it's kind of like scalar multiplication, if you will, to a vector, or it's just, if you're familiar with that terminology. If not, you're just multiplying component-wise into here. So, okay, and we can let's require H. So this map right here, let's require it to be an H. Let's require it to be a Z module map, so it preserves outside multiplication as well as inside addition. So that being the case, if we had like H of AB, where's it going to go? It's going to go to A times H of E1 plus B times H of E2. Why is that? That's because AB is this. And if you apply H to it, then what we get is, so we put all this into H, and then we end up getting H of AE1 plus BE2. And see right here, the addition can come on the outside of the H, and then outside multiplication by A and B can come on the outside. So we end up just getting, so this just ends up being this itself, just like that. Okay. All right, so then, so all we really need to know is where H sends E1 and where H sends E2, and then then we know exactly where to send every single guy in Z cross Z. Okay, so, and because we have a unique representation here, this actually uniquely determines what happens to everything. So we're completely, in fact, we can have a well-defined Z module map, and it will be a Z module map if we just decide somewhere to send this guy, E1, and somewhere to send E2, and then we can have a module map. We're done. So we just need, so to create a module map and to make sure it's a module map, when things are free and we're not modding, it suffices just to define the image of one thing and the image of another thing here in this case. So the images of like the tuples that have like a 1 in one place and a 0 another place, or 0 elsewhere. So if you just do that and decide where those go, we actually have a module map. That's all we have to do. We just have to have the images of that and then if we just say it's a module map, then we can get the images of everything else, and by construction, it ends up being a module map, and we're done making a module map that way. So it's kind of fairly easy if we just have the image of like we call these, let's call these standard basis elements. If we have the images of the standard basis elements, E1 and E2, that's enough to make a module map. Because we're free. In fact, we could say we're free to choose where E1 and E2 should go, and then H will be well defined not only as a map, in particular, it'll be well defined as a module map, as a Z module map in this case. Okay, in fact, you can, in fact, there's some checks here to make sure that it will be, and you can take a look at that. Yet, is it a module map? Okay, so does it preserve addition? So addition before, in one and only one way, this can be represented like this, which is like that. Okay, which looks like this, and then when you send it out here, this is all right. Okay, this is what it looks like. Now let's use operations in the codomain. So this is outside multiplication in the codomain, right? And it behaves this way as from its module structure, from the outside multiplication structure. And then notice, okay, so we can rearrange this. We put H1 with H2, and then we can work backwards. Notice how we put A times HE1 plus B times HE2. That's actually equal to H of AB using making the outside structure come inside, and then making it come inside here, we get this, which actually tells us, so AB plus CD becomes H of AB plus H of CD, with just a little rearranging and using our R module ideas that we were requiring for H. Clearly, it preserves addition. All right, just with that idea, and similarly here. Okay, so little terminology. Z cross Z is a free Z module, standard free basis for Z basis for Z cross Z is E1 and E2. And in general, Zn, we'll think of Z cross Z, so forth, n times, so n tuples, is a free Z module with standard free basis. Okay, so we'll call this a standard free basis. Standard free basis elements were given by tuples like 1, 0, 0, 0, 0, 1, and the rest are zeros, all the way through something like 0, 0, 0, 1. And the key idea to remember is there's only one appearing in each of these tuples, and everything else is 0. Thanks for watching.